Good morning. So today we will discuss about the first chapter of NCERT plus 1 chemistry, that is some basic concepts of chemistry. So in this chapter we will mainly discuss about the fundamentals, the basic principles of chemistry. So initially let us look what are the subtopics coming under this chapter. The first subtopic includes significant figures and their related calculations. In the second part, we will discuss about some of the fundamental laws of chemistry, that is, laws of chemistry and Dalton's theory. The third part is the most important one, in which we will discuss about mole concept, which further includes calculation of atomic mass, molecular mass, molar mass, empirical formula, AVOGADRO number, and a lot more. The last part we will discuss about stoichiometric calculations, which further includes limiting reagent concept and its related calculation. Along with that, we will discuss about some fundamental concentration terms, basically quantitative analysis, which includes molarity, normality, mole fraction. Okay. So in today's class, we will go with mole concept. Okay. You all know that the entire universe is made up of matter. Matter in turn consists of atoms. Atom combines to form molecules, compounds. So atoms are the fundamental units by which everything in the universe is made up of. And atoms are so tiny, so small, so it is very difficult to find its mass, its size, other properties. So scientists found it very difficult to study about atoms. Let's look how to calculate the atomic weight. So let's study with some examples. You assume that you have an orange with you. You have an orange. And you are asked to find its mass. So what you will do? You will take the orange, put it in a weighing pan, and you will measure its weight. And let's think you got 100 grams. So let it be orange, apple, anything. You can just take it, put it in the weighing pan, and you can get its weight. Is it possible in case of an atom? You know that a weighing pan, the normal weighing pan which is used in grocery shop can only show the weights like kg, kilograms, grams, milligrams. So it can't find the mass which is very small, in case of atoms where the mass is so negligible. So the maximum accuracy up to which a weighing machine, the normal weighing machine can measure is up to milligrams. So more small values of weights can't be measured using the normal weighing machine that we have. So the first method is not applicable in case of atoms. Let us look another way. Let us think you are having 50 grams. No, let us think you have 50 number of groundnuts. You have 50 groundnuts with you. And you put it in the weighing pan and you got the measurement like 50 gram, which shows that the weight of one groundnut is 1 gram. So 50 gram nuts weigh 50 gram. So the weight of 1 groundnut is 1 gram. So if you know the total number of entities or total number of particles, you can divide the total weight with the total number of particles to get the weight of one particles. That is weight total by number of particles or number of substance will give you the weight of one particle, right? But yes, this method is applicable in case of atom. You can take a handful of gold atoms, you put it in a weighing pan, so you will get a measurement. Let's think it is 500 grams. So you can divide it with the number of gold atoms. But the problem is, can we find the denominator, number of gold atoms? Can you find this? The number of gold atoms is not possible. With the normal method, it's not possible to find the number of gold atoms. It's impossible to pick each atom and to count how many atoms are there. It may take generations and generations of human life. That much time consuming, and that is impossible basically. So we need to think of some other alternative scientific method for calculation of atomic mass. The usual methods are not practical to measure the atomic weight. So these methods can be discarded. And finally, a scientific method of calculation of atomic masses was described. So let us study about how to calculate atomic mass scientifically. Let us consider two beakers. Let the first beaker be A, the second beaker be B. Let us fill the first beaker with some gases. Assume it as hydrogen, and the second beaker is also filled with some gas. Assume it to be oxygen, O2. And we are filling both the beakers with same volume of gases. Both the beaker has same volume of gases. And at a constant atmospheric pressure, let's say it is 1 atm, and a constant temperature, let's take it as 25 degrees Celsius. Okay. So we are conducting the experiment at a constant pressure of 1 atm and a constant temperature of 25 degrees Celsius, and both the beakers are having same volume of different gases. So my question is whether the number of molecules in both the beakers be same. That is, whether number of molecules of H2 in beaker A will it be equal to number of molecules of O2 in beaker B. So a world famous scientist, a chemist, AVOGADRO proposed the law. He said, actually in hypothesis, he said that equal volume of gases under constant temperature and pressure will have equal number of particles. So under Avogadro hypothesis, we can say number of molecules of hydrogen in beaker A is equal to number of molecules of oxygen in beaker B. So in turn, now we found that beaker A and beaker B is having same number of hydrogen and oxygen molecules. I will make it more clear. Say that beaker A is having 5 molecules of H2. So beaker B will be having 5 molecules of O2. So we are not saying anything about the mass. We are just saying about the number of atoms or molecules or particles. The number of particles will be same. So I repeat the law. When equal volume of gases are taken at a constant or similar temperature and pressure condition, both the beakers will be having equal number of molecules. So let's say this is having 5 molecules, this one will be also having 5 molecules. Since the number of molecules are same, we can say that their mass is in a ratio. And after weighing their masses, we got the ratio of mass of beaker, we are taking mass of beaker A is 1/16th the mass of beaker B. Let's say the mass of beaker B is X. So X by 16 will be the mass of beaker A. So what is the mass of beaker B? You can divide it by 16 to get the mass of beaker A. Or the other way you can say mass of beaker A into 16 will give you the mass of beaker B. So we can write that is mass of mass of oxygen atom is 16 times mass of hydrogen atom. Or else what you can write? Mass of O2, that is oxygen molecules, is 32 times. No, we can write 16 in terms of molecules. So 16 times the mass of hydrogen molecule. So the ratio between hydrogen, the mass of hydrogen and oxygen has been found out using this experiment. So using this experiment, we can find out the ratio of mass of hydrogen by mass of oxygen. I am writing in terms of atoms. So it is like 1/16. Okay. So according to Avogadro's law, we found the atomic masses with respect to hydrogen. So what we said, if we assumed the mass of hydrogen be 1 unit, that is 1 unit is the mass of hydrogen atom. So with respect to that, we said 16 unit is mass of oxygen atom, or 32 unit is the mass of oxygen molecule, right? O2 molecule. Or we said 28 unit is the mass of N2 molecule. N2 atom will be 14. So in the first method or in initial years, we calculated atomic masses in reference to hydrogen. So the initial reference was hydrogen. The reference initially used was hydrogen. Okay, but you know that there are some disadvantages in this method, or this method is not applicable in certain areas. Let us look what are the issues regarding this method. Hydrogen is not reactive with every element. Hydrogen is not reactive with all the elements. You know that we will be discussing actually hydrate gap concept in chapter hydrogen. That is, hydrogen won't be reacting with certain metals of group 7, 8, 9. They are actually D block metals, and the hydrogen won't be reacting with these metals. So that is known as hydrate gap. We will be further discussing about those in the upcoming chapters. That is, hydrogen won't be reacting with every element. The second problem, this was the first problem. The second problem is, this method is applicable in cases of gases only. You know the Avogadro's law. What does Avogadro's law say? When equal volume of gases are put in two beakers, their number of molecules are same. So this method actually was based on Avogadro law. So this is only applicable. So only applicable to gases. So other elements mass won't be able to find out or figure it with this method. So scientists gone for the next method. So next reference was oxygen. They used oxygen as the next reference, and they took mass of oxygen as 16, and this was considered as the next reference, oxygen with mass number 16. But later it was found that oxygen doesn't exist only in the mass number 16. Oxygen 17 is the oxygen 18. So now another problem arises. You know these all are isotopes. What is isotopes? Same atomic number. Atomic number is 8. So same atomic number but different mass number, isotopes. So the net or the average atomic mass we have to calculate. So we can't say that oxygen is just 16, the mass of oxygen is 16, or we can't say mass of oxygen is 17. We have to take average atomic masses in case of isotopes. And average atomic mass is calculated based on relative abundance. Their abundance, relative abundance in nature. Based on their relative abundance in nature, we took the average atomic mass. Let's say oxygen 16. Let us consider oxygen 16 is 99%, oxygen 17 is 0.8%, and oxygen 18 is just 0.2%. So based on that, we will do certain calculations which we will be studying in the next portion. And finally, we discovered that the average atomic mass of O2, that is oxygen, we will take oxygen, not oxygen molecule, oxygen is not 16, it was 16.008. It was 16.008. But this found it very difficult for using in calculations. Let's say you have to multiply, let any number, 48. You have to multiply the number 48 with 16.008. It's not so easy. We can't neglect because these are used in higher order scientific reactions or scientific equations. We have to use. So we can't simply eliminate this 8. We can't round it off like what we usually do. So this put some complications in calculations. So physicists, that is basically physics teachers or physics learners said that this method is not applicable because it's very difficult for using in calculation. So the scientists started to look for another method. Both the methods using hydrogen as well as oxygen was found to be having some disadvantages. So they finally disregarded both of the methods and they gone for the next method. So let us discuss about that. Finally, in the year 1961, we accepted using carbon 12, that is C12 isotope, to be the standard or the reference. The reference was considered as C12 isotope. Carbon 12 was taken as a reference. Initially we said hydrogen was the reference, then oxygen becomes the reference, and later on carbon 12, that is you presently followed, carbon 12 isotope was taken as the reference. Using this we will say about the mass of other atoms or molecules. If carbon 12's mass is this much, the other's mass will be that much. So with reference to carbon 12 we will say. So let us look why we took carbon 12, then its related calculations. Let us discuss detailedly on that. Let mass of carbon 12 atom in grams. Actually in grams we can find it presently using mass spectrometer. Actually nowadays science has grown a lot, so there are equipments to find the mass of atomic particles. So mass of carbon 12 atom in grams is equal to 19.93 into 10 raised to minus 24 grams, or we can write 19.93 into 10 raised to minus 27 kilogram. This is the mass of a single carbon 12 atom. Let us look what is the mass of carbon 12 divided by 12, that is 19.93 into 10 raised to minus 24 gram divided by 12. You will get 1.66 into 10 raised to minus 24 grams. This 1.66 into 10 raised to minus 24 gram is allotted with a unit which is known as 1U. This U stands for unified mass. So in chemistry, 1.66 into 10 raised to minus 24 gram is denoted using 1U. So 1U is equal to 1.66 into 10 raised to minus 24 grams. So how we got it? Initially we consider the mass of carbon 12 atom, The mass of a single carbon 12 atom is 19.93 into 10 raised to minus 24 grams. Now we divide that value with 12. Okay, we divide it with 12, that is 1/12 the mass of carbon 12 atom. That answer we got as 1.66 into minus 24 gram, and it was given with a designated with the unit 1U, or it can be written as 1 AMU, that is unified atomic mass unit. It is actually unified mass or unified atomic mass unit. So in the next lecture we will detailedly discuss about how to represent or how to describe the atomic masses with the help of unified mass, and how to convert into gram, then how to find molecular mass, then how to find molar mass. So that we will be discussing later on. Thank you.